In Module 7, we're to cover the MX6 maintenance. The MX6 was designed so that basic maintenance can be performed on the instrument, allowing for maximum performance with minimal downtime. Items like sensors, filters, battery packs are consumable items and therefore may need to be changed out periodically. The instrument itself does have a lifetime warranty and can be serviced at an authorized repair facility. To do so, we just contact Industrial Scientific Corporation at two different numbers, either 1-800-338-3287 or at 412-788-4353. Before we can really get into the maintenance of the instrument, we do need to discuss the sensor technology. The reason we have to talk about sensor technology because this is truly the heart of the instrument. It is what actually detects the gas. Considering this, though, it can also be the weak link. 9 times out of 10, when something goes wrong with the instrument, generally it's sensor related, and all you have to do is change out the sensor to make it all better again. Understanding the operations of this technology is imperative to help extend the life of these sensors and maximize the instrument's overall performance. So let's go ahead and look at the catalytic diffusion sensor. Some people call it an LEL sensor. Some people call it the combustible sensor. Regardless of the name you give it, this is a sensor that detects combustible gas. Detect any and all combustible gases because of its principle of operation on the inside. If you could see the inside of a combustible sensor, this is what you'd see. You got these two little tiny beads inside. One's a sensing bead, the other one's a temperature compensating bead. Now these two beads are manufactured with 1/1000th of an inch thin platinum wire that's spun like a coil or like a filament in a light bulb. We then put chemicals on these beads. The sensing bead is doped with 11 different catalysts to give it the ability to burn combustible gas, whereas your temperature compensating bead is coated with a material to make it blind. It can't burn combustible gas. Now when your sensor's plugged in the instrument and the instrument's turned on, these two little beads get up to 500 degrees Celsius, which is smoking hot. So when combustible gas vapors do enter into the sensing chamber, your sensing bead will start to physically burn the gas. So now I have one bead that's burning combustible gas, and I have another bead that's not burning combustible gas. What we know is that the sensing bead is going to be hotter. Whereas your temperature compensating bead may be staying at its 500 degrees Celsius reference point, your sensing bead may be 600 degrees Celsius. Alright, so now I have a 100 degree temperature difference between the two beads. How we turn that into a reading is by using something called the Wheatstone bridge circuit. Now when you look at my Wheatstone bridge circuit, you'll see that it is essentially my combustible sensor. I have my temperature compensating bead, and I also have my sensing bead. And inside the instrument are two paired resistors. So we match up the resistance on all four sides of the bridge, and that's what gives you a zero reading on the display of your instrument. It's also known as a balanced circuit. But when the sensing bead starts to physically burn the gas, heat's going to build up in this part of the bridge. Not only will heat, so will the resistance. So now my resistance is higher here at the sensing bead than anywhere else on my bridge, causing my Wheatstone bridge circuit to become unbalanced, which is what gives me the reading on a display of my instrument. Alright, so what do we need to know about the combustible sensor and how it detects combustible gas? The way it detects combustible gas is it burns the combustible gas. The greater the concentration of combustible gas, the greater the burn. The greater the burn, the greater the heat. The greater the heat, the greater the resistance. The greater the resistance, the greater the reading on the display. So if we could actually see inside of combustible sensor, this is what we'd see inside. Now we took these pictures underneath microscopes because, well, that's 1/1000th of an inch thin platinum wire. That's 7 times thinner than a human hair. Pictured on the left, you'll see I have circled, that's actually the sensing bead. Now the sensing bead is very porous, kind of like a piece of charcoal, and that is so that the combustible gas vapors will actually mix with the electrochemistry and cause a reaction. What you're seeing on the right, though, this is my temperature compensating bead. Now the temperature compensating bead, you'll notice, is very smooth. This is the close-up of the temperature compensating bead. And like I was saying, it's very smooth because we don't want any chemicals mixing with the electrochemistry. We want it to stay at one stable temperature. The thing about combustible sensors though, since it works on the principle of burning combustible gas, we have to ensure that we have at least 10% by volume oxygen available. Otherwise, the combustible sensor will either not detect or read erroneously low of combustible gases. Now, the combustible sensor inside your instrument should give you about 3 to 5 years of life. So you should get 3 to 5 years of life out of your combustible sensor. But a poison can shorten that to 3 to 5 months if we're not careful. What poisons do is they adhere themselves to catalyst bead. And they can damage all or part of that sensing bead. Our biggest poison is silicone. Silicone can be found in many different products. It's in Armor All. There's other types of silicone greases, lubes, and caulking, where if the silicone is off-gassing, you have that hot burning bead. Silicone vapors may actually melt on the bead, coat the bead, and insulate the bead. The type of damage that silicone poisoning can cause is permanent. A sensor cannot recover if it's been affected by a poison like silicone. And the reason why silicone causes permanent damage is because silicone's cousin is silica. Silica, of course, is sand. And when you superheat sand, it turns into glass. So when the silicone vapors come in and hit that hot burning bead, they form a glassy coating on the outside of that bead. That glassy coating you cannot get rid of. It's permanent damage. So we always recommend that if you think you've exposed the sensor to an agent like silicone, that you should calibrate it. The reason you should calibrate the instrument is first off twofold. One, you want to ensure that the sensor is still working, and two, previously we talked about full spans. And in full spans gives us an indication of strength of sensor. If there's a big difference of full span between one calibration and another calibration, it could be an indication that the combustible sensor was exposed to a poison. And like we were saying, we have to avoid agents that have silicone in it, most notably Armor All. A lot of people like to Armor All the dashboard, their company vehicles. Then they let the instrument sit up there in the hot August sun. Meanwhile, all that silicone is off-gassing. Over time, that may have a poisoning effect on your sensors. So we want to avoid any type of silicone-based product. Although the combustible sensor can detect any and all combustible gases, it is important to note, though, if your combustible sensor is poisoned, it'll first lose its sensitivity to methane before any other combustible gas. Not only do we have to watch out for poisons, but we also have to watch out for inhibitors. Now, inhibitors are a lot like poisons. They adhere themselves to catalyst bead. They could desensitize the bead, affecting the long-term life. But if there's one good thing that can be said about an inhibitor, it's this. A sensor can partially recover if it's been affected by an inhibitor. And how we make it recover is by calibrating it. Hopefully by calibrating it, we're going to burn off some of the inhibitors that have crusted itself on the bead. Now, the most common inhibitors we have to be concerned with are sulfur compounds. Sulfur compounds, and a lot of people get concerned about sulfur compounds because, well, whenever they calibrate their H2S sensor, they're exposing their combustible sensor to hydrogen sulfide. And they'll say to me, Brad, does that mean every time I calibrate my instrument to hydrogen sulfide that I'm going to damage the combustible sensor? And the answer is no. When we're talking about sulfur compounds, we're talking about very high levels of sulfur compounds, levels that are dangerous to human life. Not the low concentrations you find in your calibration gas cylinder or day-to-day exposures. Just to kind of give you a little heads up, a test we did at Industrial Scientific is we took a batch of our combustible sensors and we applied 1,000 ppm of hydrogen sulfide to them for 1 hour. As a result of 1,000 ppm exposure for 1 hour, the sensors lost 16% of their life. Was the combustible sensor still good? Absolutely, but 16% of their life was lost as a result of 1,000 ppm H2S exposure for an hour. We also have to watch out for leaded compounds like you find in leaded gasoline. But we also have to be concerned with halogenated compounds. Now, halogenated compounds is any type of O-depleting type gas, which then becomes very important as to what you choose to clean your instrument with. Because some people will actually use some sort of cleaning agent that has a propellant in it that is a halogenated compound. Well, best thing to use to clean the outside of the instrument is mild soap and water. That's what our repair department uses. They use 1 part Dawn dishwashing detergents and 10 parts of water, and it seems to cut through the grease the best. So we don't want to use any harsh chemicals on the outside of the instrument when we clean it. We want to stick with mild soap and water. So let's go ahead and look at the electrochemical sensor. Now when we're looking at the electrochemical sensor, now we're essentially looking at all the rest. Now if you could see the inside of an electrochemical sensor, this is what you would see inside. Now at the very top of your electrochemical sensor is something called a Teflon membrane, which allows gas to permeate down through a capillary tube. The gas will then come in contact with 3 different electrodes: a working electrode, reference electrode, and a counter electrode. And at the very bottom of your electrochemical sensor, electric light reservoir. Now your electric light reservoir holds about 1 cc of 40% pure sulfuric acid. So the last thing we want to do is go opening up these sensors to see if there's little monkeys running around inside. It's really not all that interesting inside of an electrochemical sensor, because where my gas is being detected is on those 3 electrodes. Now those little electrodes are actually Teflon coated metals. And the metals that are used are metals like gold, tin, platinum, silver, all dependent upon the type of gas it's designed to detect. In other words, the only difference between an SO2 sensor and an H2S sensor are the metal plates inside. So what we're looking at here is the cross section of the sensor. And as you'll see, once again, we have our metal plate sitting in an acid bath. Now electrochemists could talk for hours on this subject, but basically how this sensor works is it works like a battery. It's got a lot of the same components that a battery does. Your car battery, what is that? Metal plate sitting in an acid bath. And what a car battery puts out is electricity. Same exact thing about electrochemical sensor. It's always putting out a little bit of electricity. But where the electrochemical sensor is different, when the gas comes in and causes the electrochemical reaction inside the sensor to increase, it's going to cause more current to be released, proportional to the amount of toxic gas it's designed to detect in the environment. And whether an electrochemical sensor is sitting on the shelf or sitting in the instrument, it's degrading at about the same rate. So this is one reason why we always recommend that you calibrate your instrument once a month. We know that inside that sensor, those metal plates are under assault by the acid. We know that inside there the chemicals are changing. Therefore, monthly calibrations are a necessity to ensure that that output current is being adjusted by the instrument's electronics to compensate for any lost signal over time. Now the reading will not appear instantly on the display of the instrument when you're dealing with electrochemical sensors. It takes a little bit of time for that reading to appear. This is what we call the T90. This is the amount of time it takes for 90% response. Typically on a new electrochemical sensor, we're going to receive 90% of that response to that sensor within the first 30 seconds. But it may take as long as 2 minutes to get the entire reading on the display of my instrument. For example, let's say you go into an environment and in that environment is 200 ppm of carbon monoxide. Your instrument should be reading somewhere around approximately 180 ppm within the first 30 seconds. Now to get the full 200 ppm response may take as long as 2 minutes. And what you're seeing up here is a list of all the different electrochemical sensors that were for the MX6. And as you'll see, there are 12 different electrochemical sensors. Now you'll notice down the lower right hand corner is an example of one of those sensors, and what you see is a sensor we call a COSH sensor. This is a CO H2S sensor that's blended into one, so it independently monitors for both CO and H2S in one sensor package. Now the MX6 is a 6-gas instrument, but you'll notice when we open it up that there are only 5 ports to plug in sensors. Which means to make the MX6 a true 6-gas instrument, 2 of the gases I'm monitoring for must be CO and H2S blended in one sensor, and that sensor is called a COSH sensor. Let's go ahead and talk about infrared sensors a little bit. Now, infrared sensors are completely different from your electrochemical counterparts. I mean, this technology is used in applications where catalytic diffusion or electrochemical sensors will not work. This type of sensor is available for detection of either of the following. We use this for detection of CO2, carbon dioxide, and we also use it for detection of methane, up to 100% by volume. Now, why do we use infrared sensors for detection of CO2 and methane? Well, with carbon dioxide, the gases cannot be easily detected by using electrochemical technology very well. Infrared sensors have superior capabilities for detection of carbon dioxide over electrochemical sensors for that carbon dioxide. And for methane, well, we know that the catalytic diffusion sensor can detect methane, but if I want to detect methane up to 100% by volume, I can't use the catalytic diffusion sensor because remember, it needs at least 10% oxygen. So if I want to detect methane up to 100% by volume, naturally there's going to be no oxygen. Therefore, the infrared sensor becomes indispensable. So basically, how do these sensors work? Well, they're based on the principle that all gases absorb light energy, and they're going to absorb this light energy at a specific wavelength. If we know what this wavelength is, we can look for the absorption of gas out on that spectrum. And gas concentration is proportional to the amount of light energy absorbed. The more of that light energy absorbed, the greater the gas concentration. So as we're trying to detect methane, we have to look out on the infrared spectrum to see where methane peaks. You'll see there in red, that peak right there at a little over 3 micrometers is actually methane, and that's where the greatest absorption of methane is going to occur, is at 3 micrometers. So we have to tune the optical sensor inside the infrared sensor to look at that 3 micrometers of light. The more of that light energy the infrared sees, the less methane gas. Why? The methane will absorb that light energy at a little over 3 micrometers, but the more of that light energy it sees, the less methane in the environment. And now let's talk about our last sensor technology that can be installed in the MX6, and that is our PID, otherwise known as a photoionization sensor. Now, this technology allows for detection of volatile organic compounds. These are also known as VOCs. Now, people will then ask, well, what is a VOC? Well, a VOC is any carbon-based molecule that is in a gaseous form. Examples of these VOCs are things like benzene, toluene, xylene, pentane. In fact, there are hundreds of thousands of VOCs out there. So why not just use the LEL sensor for detection of VOCs? Well, the catalytic diffusion sensor is great at detecting VOCs, but only in the LEL range. But many VOCs are toxic down in the part per million range. Let me give you a good for example. Benzene. Benzene has a permissible exposure limit of 1 ppm. Can the combustible sensor used in the MX6 detect benzene? Absolutely. But by the time you get a 1% LEL reading on a display, you'll be in a world of hurt. So now I can look for the toxicity of these VOCs rather than the combustibility. Therefore, to detect V's in the parts per million range, the PID sensor is the best sensor choice of detection. And another big bonus of the PID is I can now detect these VOCs all the way down to 0.1 ppm. So it gives me extended resolution. Okay, so how does a PID sensor work? Well, inside your PID module that you'll see located down there in the lower right hand corner is what's called a 10.6 electron volt lamp. What this lamp does is it produces ultraviolet light. What the ultraviolet light will do is ionize the gas. When the gas gets ionized, it's going to take on a positive charge. inside that PID sensor is electrodes. And what those electrodes are going to do is detect the ionized gas by attracting that ionized gas to the electrodes to determine the gas concentration in the environment. And this will once again read all the way down to 0.1 ppm concentrations. So in essence on the PID, it all comes down to photon energy. If the photon energy of the lamp is greater than the ionization potential of the gas, then the gas will be ionized. Therefore, any gas with an ionization potential of 10.6 or less can be ionized. Since sensors are consumables, they do have a life expectancy that is best determined during calibration. We never want to try to time change out our sensors or battery packs. Rather, we want our calibration to determine when these sensors ought to be changed out. But there are date codes on the sensors that can help us determine if the sensor may be within or past its warranty. So when we're looking at the catalytic diffusion sensor, remember this is your LEL sensor. If we want to read the date code of the sensor to see when the sensor was actually manufactured, we're going to use the serial number, and it reads year and month of make. So in this example, we see the first four numbers of the 0701. That would indicate to us that the sensor was made in 2007, first month. So that'd be a January 2007 make. Now, electrochemical sensors are a little bit different. To read the date code of your electrochemical sensors, we're now going to use the last three numbers of the serial number, and it goes month and year of make. So looking at the last three numbers here, we see 017. That would indicate first month, January. 7 would indicate 2007 when the sensor was made. Now for some of your more exotic toxics, gases like hydrogen chloride, hydrogen cyanide, ammonia, chlorine, chlorine dioxide, the way you read the date code in these sensors are a little bit different. Once again, you're going to use the last three numbers, but it goes year and week of make. So what we see here is the sensor was made in 2007. That's what the 7 would indicate, and the 22 would indicate to us 22nd week. When we're looking at lithium-ion battery packs, they are also consumable and have a life expectancy of only about 4 years. A date code can be found on the battery pack to help determine if the cells are past or within its warranty. So first we'd have to do is take off the battery pack, and underneath the battery pack we're going to see a barcode. Underneath the barcode is where we're going to see our serial number. We want to look at the first four numbers. First two numbers are the year, second two numbers are the month of when the battery pack was made. So the example that we see here is 0704, and that would indicate the fourth month, which is April, and the 7 would indicate 2007. Now the MX6 has a lifetime warranty on it, but still provides a manufacture date located in the bottom of the instrument if you need to see when the instrument was actually manufactured. So down where the contacts are, the charging contacts, you'll see a barcode once again, and you read it the same way as the batteries, first four numbers. And it'll go year and month. First two numbers are the year, second two numbers are the month of when the instrument was made. So let's look at how you remove a battery pack. To remove the battery pack, the first thing you have to do is loosen the 3 captive screws on the back side of that battery pack. Once those 3 captive screws are fully loosened, you'll be able to remove that battery pack. Now, screws are captive, which means they should stay with the battery pack. But once all 3 are fully loosened, then you'll simply be able to lift that battery pack off the back and place it off to the side. Now at this point, if we wish to remove a sensor, that can be done by first loosening the top screw, which is also a captive screw. Once we have that screw fully loosened, you can remove the sensor cover. With the sensor cover removed, we can now remove a sensor by first grabbing that sensor, give a little bit of a wiggle, and then you'll be able to free it from its connector. Now if we want to put a sensor into the instrument, we could take that sensor. You got two contacts on the bottom of the sensor. You want to make sure you match that up with the contacts inside the instrument, and then it should just easily plug right into place. Now the MX6 has the ability to accept up to 5 sensors at a time, and that is of the 25 different sensor types available. But of these 25 sensor types, there are 4 that we call power sensors. Now the 4 power sensors are the catalytic sensor, CO2 IR, methane IR, and the PID. Now the MX6 can only accept 2 power sensors at a time. In other words, I cannot configure my MX6 for LEL, CO2, and PID. Only 2 power sensors can be placed inside the instrument. We also have to ensure that when we put power sensors in the instrument that we put them in the correct spot. Power sensors can only be installed on the right-hand 2 slots. The combustible sensor must be placed in the lower right-hand position. If I put the LEL sensor in any other position other than the lower right hand, or the PID not in its proper position, when I turn on the instrument it will tell me illegal configuration. Okay, so let's look at reassembling the MX6. First we put our sensor cover on. Once we have the sensor cover on, we can now tighten up our Phillips head screw. Once that screw is fully tightened and in place, and not over tightened, just to the point where it's snug, we can then put the battery pack back on. Once again, we got the 3 captive Phillips head screws, and we just tighten those until they're snug. We don't want to over tighten these. And once they're all in place and fully tightened, the instrument will be fully reassembled. Let's look at removing a sampling pump. If I have a sampling pump in my MX6, I can remove that sampling pump to make it a diffusion instrument. The first thing I must do is, of course, fully loosen the 3 captive Phillips head screws on the back of the battery pack. Once those are fully loosened, I will then be able to remove that battery